All right, welcome back. We're going to start with Unit 3, which is all about stateful sets. So we've been using deployments, and deployments are great. We even, sort of have Drupal running in Kubernetes already. What the heck? But there are still some problems when it comes to deployments. So we have Drupal. Drupal's going to talk to a deployment that has 3 MySQL replicas in it. And again, they have those non-deterministic host names. Now you might think, right, so which one of these is Drupal going to talk to actually get our MySQL connection? Well, we could put a service and a load balancer in front of it, sure. So what would that look like? So Drupal says, insert something into table X. Okay, fine. The first database gets, MySQL pod gets that request, goes OK, inserts it into the file, into its own disk, and says, sure, all good, query's fine. Then later on, Drupal will say select from X, but this time the load balancer says, well, we're not talking to that MySQL server anymore. The next one in the queue is the next one over. So we're going to send this select request to that one. And when that happens, it's going to return an empty set because each one of these pods has its own disk. And this becomes a huge problem because now we don't know where the data went. Where's the data? What happened to it? Is it gone? And it's not gone, it's just on one of these 3 pods. So the problem is that with load balancing, not all apps are really compatible with it. Load balancing databases is extraordinarily difficult, and it actually becomes very difficult with MySQL. There are mechanisms to actually do it, but they require some very complex setups in the back end in order to make it work functionally. So as a result, it's just not an application which is easily or really practically load balanceable unless if you want to dedicate an enormous amount of time to it. So we really can't use a service and a load balancer. Wouldn't it be easier if we just had some predictable host names? Drupal supports multiple MySQL connections out of the box. One writer, multiple readers. Sure, we could do that. Wouldn't that be so difficult? This way, Drupal can go insert into X, and it can get the query directly from that pod without needing to go through a load balancer. But deployments don't let us do this because it doesn't let us turn off non-deterministic host names. So what we really need in order for a non-load balancer application to work is a predictable host name. And the problem is this is not possible with deployments because the fundamental configuration of deployments is to have non-deterministic host names. So are we screwed? Can we do anything about this? Well, actually, yeah, we need something slightly different than a deployment. It's called a stateful set. A stateful set is intended for stateful applications inside Kubernetes. And stateful means that when it receives a request, it has an internal state which will determine the external output of that request. So with a web server, it's assumed that as long as the HTML files don't change, the application always produces the same output for the same input. But a database, some of that input could modify the data that's there and then produce different output for a succeeding query. That's what a stateful application is in terms of Kubernetes. So a stateful set definition is right here, and it looks pretty much a lot like a deployment. API version apps/v1, just like a deployment. The kind is different, obviously. It's not deployment, it's stateful set. It has a metadata section, it has a spec section with a selector, match labels, and then it's got this other line called service name. That's different, but let's put that down for the moment. Let's keep going. We'll keep looking down the rest of the file. Replicas equal 1. It's got a pod template, just like every other deployment we've ever worked with. Metadata labels app equals MySQL, just like our selector up there, and a spec section with containers. And we have one container in here that's called DB that is running 10.7/flightdeckdb. And it's open port 3306 inside of the cluster, like you would expect. Okay, so it looks just like a deployment. That's great, except there's this one line. So it's like a deployment, And with it, you can work with it just like a deployment. Kube control get stateful sets, kube control describe stateful set, kube control edit stateful set. Every command you've used to work with deployments will also work with stateful sets. But stateful sets have a number of nifty little tricks up their sleeves, which make them perfect for things like MySQL. They're fault tolerant. Anytime that we have a series of stateful set replicas running the same stateful set, if one of those fails, a new pod doesn't get created at the end of the list and that crashed one removed. No, that crashed one is removed and then a new one assumes its place inside the same location within the cluster. This includes host names and critically volumes. So this way, when you say there are 3 replicas of the stateful set, MySQL-0 always exists, -1 always exists, and -2 always exists. And if one of them fails, a new one steps up to take its exact place like nothing ever happened. So services sound great. Do we need a service? I mean, stateful sets sound great. Do we need a service? Well, the answer is yeah. Yeah, we do need a service because a service advertises network accessibility. Despite the fact that we're going to actually be talking to the stateful set pods directly, we do need to tell Kubernetes that they are accessible, that they are available for people to access so that we can assign a DNS name to them so that people can actually find them. The trick is that we want to make sure that we need the service definition so that it defines it to Kubernetes, so Kubernetes knows it exists, but not use any load balancing at all. How in the heck are we going to do that? What we need to do is create a headless service. It advertises access, but doesn't have any load balancing. So this is what a headless service definition looks like. And why don't you take a second here to actually see if you can guess what makes this a headless service versus the service definition that we saw earlier. So you're probably looking right here at cluster IP equals none, and you are correct. That is what makes this a headless service. Cluster IP none turns off any load balancing. It looks really weird in Kubernetes because, wait, aren't I supposed to have an IP address here? And you say none? Well, that means turn it off? Yeah, I know. It's very strange, but this is exactly how you're supposed to create a headless service in Kubernetes. Cluster IP none. Looks weird, but okay. So that's stateful sets. But we still need one more thing in order to run MySQL and Kubernetes. We need storage to be attached to that. So we have Drupal and we have our stateful set for MySQL, and it's running 3 replicas of our pods. And what we need to do is we need to have some storage attached to these pods. So whenever Drupal makes a request, instead of the MySQL pod freaking out because it doesn't know where the data is, it will have its own persistent disk attached to it so that it can query that to read the MySQL files necessary to fill the query and return the data back to Drupal. So what we need, these are called in Kubernetes is a volume. A volume is managed disk storage. It's allocated as an object, but it is mounted in a pod. How do we allocate these things? There are actually 2 different ways. We could use a persistent volume claim. It's called a PVC, not a pipe. Or we could use a volume claim template on a stateful set. Now, a volume claim template allocates a disk for each replica, which is perfect for stateful sets because if one of them dies, a new one assumes its place. And the disks are reattached if the pod is deleted or restarted. So that's perfect for us in a MySQL replicated setup where we have one writer pod and multiple reader pods for performance. So here's what that's going to look like. We have kind stateful set, name MySQL. The rest of the spec goes here. And at the bottom, we have a volume claim template. And this volume claim template has its own metadata section. And it's going to say, we're going to create a claim called vol-MySQL. It's going to have an access mode called read-write once. Then we're going to request some resources. In this case, 10 gigabytes of storage for our database. That should be plenty for a reasonably sized Drupal site. Okay, perfect. So what about that shareability line? It's defined by access modes. Now, this sounds great. We should be able to just define one shared volume and then share it between all of our pods, right? That would work, right? Not really. The problem is that most managed Kubernetes hosting providers do not support multi-writer. Instead, you only get one writer pod for one disk. And this becomes a limitation for us when it comes to MySQL. So we can't really do it like that, but we'll show you ways of working around that. So, what about the request section? It specifies how to allocate the disk. This includes size, class, and other host-specific options. Now, size is obvious, but class? What's this? This is kind of a little bit more archaic of a bit of data that you've actually seen, you see in much more complex hosting providers. DigitalOcean doesn't really use this, but some hosting providers will offer different storage tier classifications depending on if it's SSD, high-end SSD, backed up SSD, RAID-based, spinning disk, a whole bunch of different options for storage. And those are generally considered a class of storage. Once we have the disks actually allocated, we need to mount them inside the pod. So in order to do that, we're going to modify our stateful set definition to mount them inside the pod. So we have our stateful set definition, and everything looks the same until you get down to the containers section. In our pod template, we have a new section which is called volume mounts. And right now, this volume mount, we have one mount which is going to look for a claim which is called vol-mysql, and we want to mount it in the default MySQL path of /var/lib/mysql. And this is where our volume claim gets turned into a real disk and mounted inside the pod for actual use. So you might wonder, now we have a pod we have our pods, we have disks attached to them, everything's hunky-dory. Now we need to worry about permissions. So really, who owns the disk when we allocate one of these? And because this is generally a Unix-flavored environment, the honest truth is that root owns the disk. This is not really useful for us because of one other really important best practice piece of advice, which is that most containers, in fact all containers, should never run as root. So the disk we just allocated for our pod to use, we can't use because we don't have permission to write to it. That's kind of garbage. How do we fix that? Well, what we need to do is the official way is to mask ownership. This mounts the disk as a group and then runs the user in our pod as part of that group. And how it looks like is here's our deployment definition. If we scroll down, you'll actually see there's under our spec section in our pod template, we have a new security context thing. And our security context area also has another line called FS group, which specifies which group ID to mount the disk as. So the security context allows us to set special permission options. FS group masks the disk and applies a group ID to the user and to the disk itself. Now, this group ID isn't a group name because it's Kubernetes, it's Unix. Names don't really mean anything beyond one system, but the group ID can be unique from system to system to system and becomes a consistent ID that you can pass around. Typical IDs I've seen in these configurations are 1000, 2000, 3000. Now, that's the official way to do that, and sometimes it works, and sometimes it doesn't. So what happens if we need to brute force the situation? Well, honestly, the real solution is, wouldn't it be great if we could get another container that's its only job is to start up and run as root, to own every file in the mounted volume, and then stop without making any other network connections? Wouldn't that be great? That would solve all of our problems. And the answer is, well, guess what? We can do that. It's actually called an init container. So down here we have an Init Containers section under our pod template spec. We have this Init container is going to be called fixed PVC permissions. It's going to run the base Alpine image, and it runs a single command. So it runs in the shell command, the command chown -r 1000 var lib mysql. In other words, change the ownership of var/mysql to owner 1000. Now, init containers are different than regular containers. An init container runs before any other containers. It does not make any network access, and it must run in order as defined and then stop. If it doesn't stop, the pod will never finish starting up, and your actual container will never actually start running. This way, it's a secure method of actually doing any of these initiation tasks before allowing network access and closing potential security loopholes. All right, so we have our stateful set, we have volumes attached to that. Do we get to manage these volumes too? The answer is yes. So no matter how you define a volume in Kubernetes, either a persistent volume claim or a volume claim template, these are templates that create a persistent volume object. They're like the deployments to the pods. The persistent volume, in this case, is the pod, the actual thing that represents an actual piece of infrastructure. And this persistent volume object represents, in this case, a physical disk. Claims aren't disks. They request storage. They don't embody it in Kubernetes. A persistent volume does. It represents fulfilled claims, and importantly, they are not deleted when you delete the claim or the stateful set with the volume claim template. Now, this is intentional because it's a data saving procedure. How do we manage these volumes? Kube control get persistent volumes, or honestly, that's a lot to type in. Wouldn't it be easier if we could just use a shorter version so we don't have to waste our fingers? The answer is you can do that too. Kube control get PV. These short names for the nouns are actually all over Kubernetes, and I don't use them by default because it's important to list them all out in the full word to build up that muscle memory. However, as you go on, it will get really annoying to keep typing them all in, and persistent volumes is just too darn long. So let's just use get PV. So kube control, kube config, get PV, and we'll notice we have one persistent volume claim. It's going to have a capacity of 10 gigabytes. Its access mode is read-write once, which means that one pod, and only one pod, has read-write access to it. And it has a state at the end that's called bound. Now, this bound state means that currently there is a pod that is running that is actually accessing this persistent volume. And we can even see what the claim is. In this case, it's going to be the claim template on the stateful set. So what happens when we delete our stateful set? We don't need it anymore. And we delete our persistent volume claim. We don't need it anymore. The disk still stays around. The persistent volume object still stays around. So to delete it, we must delete it explicitly. And don't do this from the web portal. It sounds really easy to go to the web portal, go to manage volumes, and then just find it and delete it. But this is actually a very bad idea with Kubernetes. Instead, you want to delete it through kube control instead. And the reason why is it deletes the persistent volume object, and then that tells the orchestration system to delete the physical volume at the managed hosting provider level. In that way, everything is nice and clean. So don't use the portal to delete a dangling persistent volume, because otherwise you'll get some problems. Also, make a backup first if you possibly can, because Kubernetes doesn't have an undo. Once you delete a persistent volume, it's gone. It's not coming back. How do you delete a persistent volume? Pretty much like you would expect, kube control, pass your kubeconfig file, delete PV, and then the name of the persistent volume. And also read this command. Whenever you use delete as a verb, read it very carefully out loud to yourself slowly, because if you make a mistake and type in the wrong object, it's going to ruin your day very quickly. This command has no "are you sure?" It will just do it. All right, it's time for lab 3. We're going to create a stateful set, we're going to observe the differences in deployments, and we're going to add a persistent volume. So let's go.